Hi there, welcome to Fusion School another video. Topics covered in this video are electric field lines and polarization. Let's start with electric field. Force per unit positive charge is called electric field. Electric field equals to force upon small q charge, where small q is the charge on which we find electric field. The dimensional formula of electric field is ml t-3 a-1. For practical calculations, test charge small q should be very small so it cannot disturb our main charge distribution. E equals to F upon Q, limit Q tends to 0. Force on any charge small q in presence of electric field E vector is equals to Q into E vector. Electric field of a point charge capital Q. Finding electric field at point A due to point charge capital Q. As we already know, force on unit positive charge is electric field. So let's take a unit positive charge at point A. Electric field equals to force on that charge, which is equals to kq unit positive charge upon r square. Direction of electric field. Direction of electric field is radially outward for a positive charge and radially inward for a negative charge. Suppose we have a positive charge and external electric field is applied from left to right. Now we are going to discuss what happens to this charge. If the electric field lines are coming from left and going right, then that means either a positive charge is present in the left side or a negative charge is present on the right, or maybe both. So the positive charge will move right. So we can say that direction of force on positive charge in an electric field is always in the direction of electric field. In this case, if we had taken a negative charge, then it would have moved towards left, that is, towards positive or away from negative. So we can say that direction of force on negative charge in an electric field is always opposite to the direction of electric field. Electric field lines, also called as electric lines of force. It is an imaginary concept given by Michael Faraday. Electric field lines always represent resultant electric field. At any point, tangent on electric field line gives the direction of resultant electric field at that point. Two electric field lines can never interact each other because at one point two directions of resultant electric field are not possible. In any diagram, number of electric field lines are proportional to charge. So here Q1 is greater than Q2. Electric field lines always forms open curves. That means they can form a closed loop. They originate from positive charge and ends in negative charge. Uniform electric field lines are represented by equally distant parallel lines. In uniform electric field, direction and magnitude of field remains constant. Let's solve a question. Which of them represents uniform electric field? Let's mark points A and B in diagrams. On moving from point A to B in first and second, the intensity of electric field line changes. Thus the electric field is not constant. On moving from point A to B in third, the intensity of the electric field lines is constant and the direction of electric field lines is also constant, so it shows uniform electric field. In fourth, the direction of electric field is constantly changing. High density of electric field lines represent high magnitude of electric field. In this case, electric field at A is greater than electric field at B. That's because the intensity of electric field lines at point A is greater than the intensity of electric field lines at point B. In this example, electric field at A equals to electric field at C, while these two electric field intensities are greater than the electric field intensity at V. This is a normal atom in absence of electric field. When we apply electric field, the electron cloud surrounding the nucleus becomes distorted. This is what happens inside a substance when electric field is applied. The atoms become polar and induce an electric field opposing the applied electric field. Net electric field inside that substance equals to applied electric field minus of induced electric field, which is equals to applied electric field upon relative permittivity. On solving it, we get induced electric field equals to applied electric field का whole into 1 minus 1 upon relative permittivity. If the substance was metal, for metal relative permittivity is infinite. So induced electric field equals to applied electric field. So net electric field in the metal will be 0. This is called as electric shielding. In this given diagram, net force on Q0 charge inside a metallic hollow sphere is 0. Force on Q0 due to only capital Q is not equals to 0. This is because it's the conductive hollow sphere that makes the force equals to 0 by inducing equal and opposite electric field. A charge given to a conductor always appears on the surface of the conductor. Well, that's because due to repulsion, direction of electric field from the surface of any conductor is always perpendicular to its surface. Metals are induced due to free electrons, while nonmetals are induced due to polarization of atoms.